Hi everyone, now we are analyzing CSIR June 2012 Chemical Sciences. Just watch the video completely, get the good information from it. And just look at the first problem. In the reaction A and B, so just check the reaction type A and reaction type B. Here in these two reactions, water behaves as acid in both A and B reactions, acid in A and base in B reactions, a base in A and acid in B, and a base in both A and B reactions. Now just come to the first reaction type A, where water is reacting with Cl minus. Okay, just try to draw the structure of water and Cl minus. These are the two substrate reacting. And for example, if we thought that the lone pair of electrons and oxygen donating to Cl minus and making a bond, in that case water should act as a base. But this is not happening because here the lone pair of electrons and oxygen and the negative charge around the chlorine makes repulsions. Okay, makes repulsions. That's why. So this type of interaction is not possible between water and Cl minus. But here, if you look at the water again, here oxygen gets negative charge and hydrogen gets positive charge. That means the dipoles can be observed on oxygen and hydrogen in water. In that case, one of the hydrogen with positive charge and oxygen with negative charge, and here you can see ionic dipole interactions can be observed between Cl minus and H plus of water. So the interaction here takes place between H plus of water and Cl minus. That means here the H plus is simply like donating to Cl minus. So whenever H plus is donated, according to Brown-Lowry theory, it is acting as water. Acting as acid. So here water is simply by just donating its proton, not completely. So just the thing that ionic dipole interaction between H plus and Cl minus, making that water just like donating its proton to Cl minus. That's why water is acting as an acid in first reaction. Okay, now just come to the second reaction, where magnesium plus 2 reacting with 6 moles of water, making magnesium complex. Okay, just observe here, and there is no change in oxidation state of magnesium in substrate and in the complex. Here plus 2 oxidation state, and here is also plus 2 oxidation state, because water is a neutral ligand. Okay, right. Now here the lone pair of electrons and oxygen coordinate with the orbitals of metal, that is magnesium plus 2, and making a complex. Okay, so whenever electron pair is donated, then we call it as a Lewis base. Okay, so that's why here in the second type of reaction, that is B type of reaction, water is acting as a base, where in the first reaction water is acting as an acid by donating its proton. So that is by just making ion dipole interaction with Cl minus. Okay, next one, the size of the d orbitals in silicon, phosphorus, sulfur and chlorine follows the order. Atomic size decrease from left to right in periodic table, we know that. Okay, so because the interaction between nucleus and outermost orbital increases by just electrons are added continuously whenever we move from left to right in periodic table. Okay, that's why interaction between nucleus and outermost orbit increases and the size decreases. Okay, so that is a simple concept we can get from the periodic table. And here if you look at the d orbital size from left to right, the size of d orbitals increases. Okay, just keep this point in your mind. And why the d orbital size increases? Because we know that whenever we move from left to right in periodic table, from the d1 electron 1 2 3 to 10, so whenever electrons increases from 1 to 10 in d orbital, the electronic repulsions are also possible in d orbitals. So whenever electrons continuously increasing from left to right in periodic table, then so that leads to increasing the size of d orbital. Okay, so here by this concept we can say that the d orbital size is highest in silicon, followed by phosphorus, followed by sulfur, followed by chlorine. Okay, yeah. And next one, the correct structure of basic beryllium nitrate. So the first one is the correct structure of basic beryllium nitrate. Okay, yeah. Next one, the total number of lone pairs of electrons in I3 minus is, so we have a simple formula. So in I3 minus we have iodine as a central atom and which has 7 valency electrons, and I3 minus species is having minus charge. That's why we need to consider another electron. So total 8 electrons are there as valency electrons, and it is making 2 sigma bonds with 2 iodines. Then we have remaining 3 lone pair of electrons. Okay. If mass Bose spectrum of FeCO5 is recorded in the presence of magnetic field, the visual spectrum with 2 lines changes into the one with. Okay, so here in the magnetic field we need to observe mass Bose spectrum of the iron carbonyl in the presence of magnetic field. Okay, in that case iron having plus or minus half nuclear I value, okay, nuclear quantum number value, its ground state, and its one of excited state it has a plus or minus 3/2 nuclear quantum number. Okay, so that's why we need to take energy differences between plus half to plus or minus half to plus or minus 3/2, and here we have the selection rule, that is delta ML should be 0 or plus or minus transitions. Okay, so by just using this selection rules, so the 6 possible transitions are observed. From that 6 lines are observed in mass Bose spectrum of iron carbonyl. Okay, that is in the presence of magnetic field. Next one, the spectrophotometric response for the titration of mixture of Fe plus 3 and copper plus 2 ions against EDTA is given below. So here in this complexometric titration, iron plus 3 is with impurities like copper plus 2, and whenever we take the titration of this mixture with EDTA, first iron plus 3 reacts with EDTA or makes a complex with EDTA, and which is a stable one when we compare with EDTA copper complex. Okay, so in the first step of the titrations, A, B indicates simply iron plus 3. Okay, so sorry, here iron plus 2 and followed by sorry, here this is iron plus 3. Okay, so iron plus 3, A and B, A to B indicating that iron plus 3, and which is making iron plus 3 into a stable complex. In the second step, CD indicates excess amount of EDTA, and that excess amount of EDTA reacts with impurity like copper plus 2 and making the complex with it. Okay, copper EDTA complex. That's why here AB indicating iron plus 3, and whereas C and D indicating excess EDTA, and which will react with the impurity copper plus 2. Okay, and makes the complex. Next one, in carbon dating application of radioisotope C14 emits, so simply beta particle is emitted by it. Okay, beta particle emitted by it. And next one, the actual base pair present in the double helical structure of DNA containing adenine, thymine, cytosine, guanine, or simply ATGC. So you can see the actual base pairs are AT and GC. That is the fourth option is the correct one. The oxidation state of iron in methemoglobin is, so iron plus 3 state is observed, that is abnormal state in methemoglobin, okay, and which is in blue color, whereas the normal hemoglobin contains iron is in plus 2 oxidation state and which is in red color. Okay, and here methemoglobin binds with cyanide and makes cyanomethemoglobin, and which is non-toxic in nature, and at the same time inorganic nitrates produces or promotes iron plus 2 to iron plus 3. Okay, just keep these points, important points regarding methemoglobin. And here NADH dependent, okay, NADH dependent methemoglobin reductase converts methemoglobin to hemoglobin. Okay, right. Next one, the reactions of nickel tetracarbonyl with the ligand. So just observe, we have given with 2 types of ligands and the yields the nickel complex. Here the reaction is associative, dissociative, interchange, that means associative interchange, here dissociative interchange. So if you look at the given carbonyl of nickel, which is 18 electronic species, at the same time these 2 complexes maybe following first order kinetics, and here due to its 18 electronic species, so in the first step simply one of the ligand, that is CO, cleaves from it, and which is a slow step, and followed by the fast reaction where trimethyl phosphorus ligand coordinates with nickel. Okay, so simply a dissociative type of mechanism is observed in this reaction. Okay, next one, as a ligand Cl minus, simply a sigma donor and a pi donor. Okay, third option is the correct answer for it. The correct d electronic configuration showing spin orbit coupling is, okay, so if T2G is unsymmetrically filled, then so that simply shows spin orbit coupling, and second and in fourth one, T2G with 6 electrons and T2G with 3 electrons, that means symmetrically filled. Whereas in first and third one, T2G unsymmetrically filled, then which one is the correct answer? Simply third one is the correct answer, because here in the first one, so here in T2G 3 electrons, in EG 2 electrons, right? In the first step 3 electrons here and 2 electrons here, that means symmetrically filled followed by next electron in T2G, making unsymmetrical. Okay, that means in the first step it is following, it is simply filling symmetrically. That's why the first configuration is not allowing spin orbit coupling, whereas in third option it is having 4 electrons. So okay, in 4 electrons in T2G, so simply, and 0 electrons in EG, that means due to the strong field effect of ligand, all the 4 electrons in T2G only and 0 electrons in EG. That's why we can consider T2G is unsymmetrically filled in third one. So that's why spin orbit coupling is observed. Okay, so that's why here third option is the correct answer. Next one, the correct statement for the aggregating nature of alkyl lithium reagent is, so the carbene ion nucleophilicity increases with aggregation. The observed aggregation arises from its electron deficient nature. Carbene ion nucleophilicity doesn't depend on aggregation. The extent of aggregation is maximum in polar dative solvents. So the second statement, the observed aggregation arises from its electron deficient nature. Okay, so we can observe alkyl lithium just like this in a cube structure where lithium makes a bond like a 2-centered 3-electron bond due to electron deficient nature. Okay, so that's why here second option is the correct answer. Next one, for the reaction, just observe reaction here, the correct observation here. So iridium in the first as a substrate with 4 coordinated, and here iridium is in +1 oxidation state only because CO and triphenyl phosphines are neutral ligands and Cl is -1. That's why iridium gets +1 charge in it. But in the product, you can see we have 3 chlorines and the complex is with minus charge. That's why iridium with +3 oxidation state. Okay, -3 and here +3. So that means simply +2 oxidation state. Oxidation state is increased from substrate to the product. Okay, whenever oxidation state increased on the central transition metal complexes, in that case the back donation from the transition metal to that means carbonyl ligand decreases. Okay, whenever electron density around the metal decreases, then back donation decreases from metal to electron withdrawing ligands like CO. Okay, whenever back donation decreases from metal to CO, then the frequency of CO increases. Okay, that's why the product frequency, the frequency of CO of product is greater than frequency of CO of reactant. Okay, we have so many concept lectures and so many problems on this kind of problems. Okay, just check them. Next one, the nucleophilic attack on olefins under mild conditions. So simply nucleophilic attack on olefins increases, or simply it requires activation by coordination to metal. Why? Because here the simple alkene act as a nucleophile. Okay, in general the normal alkene act as a nucleophile. So to attack nucleophile, external nucleophile and onto normal alkene, the alkene should coordinate with metal. In that case, the electrons are dragged onto metal. So that's why external nucleophile can attack on nucleophile. That means here the nucleophilic attack on olefin require activation by coordination to metal. Okay, so fourth option is the correct answer. Next one, among the following, the strongest oxidizing agent is. So just check the oxidation states of metals in the given four options, and if you look at them, all of them having same oxidation state, that is +6. Okay, then if you look at the size of those metals, chromium +6 is having smallest size. Whenever smallest size is there, then electron attracting capacity increases. Okay, electron attracting tendency increases for that smallest sized metal. That's why the strongest oxidizing agent is the second one. Okay, next one, the least basic among the following is. So if you look at aluminum hydroxide, which is amphoteric in nature, that's why it is least basic in nature. And if you look at all the lanthanides or bases. Okay, for any operator A and its adjoint, just observe its adjoint, the incorrect statement is. So the first three relations are Hermitians. Okay, whereas fourth one is anti-Hermitian, because here Hermitian operator should follow this relation, whereas if you look at the fourth one, by just taking adjoint of it, then it is producing anti-Hermitian. So that's why fourth option is the correct state or correct one for the given problem. Okay, right. Next one, for hydrogen-like atom with a nuclear charge, the energy of orbital with principal quantum number n follows relation. So we have the formula, that is E equals to minus 13.6 into z square by n square. So from that we can get minus z square by n square. Next one, the average value of the radius in the first state of the hydrogen atom is here A0 is Bohr radius. So just take integrations of the wave functions of 1s orbitals with the operator or caret. Okay, by just applying and solving, we can get 3 by 2 A0, which result simply 1.5 A0. Okay, so here one should have mathematical basics. Just look at the mathematical basics for the physical chemistry in our courses, and you can get the best concepts from them if you are from non-mathematics background. Okay, if you are from a mathematics background, I think it will be useful for you to solve it. Okay, yeah. Among the following, the correct statement is the number of irreducible representations is equals to classes of symmetry operations. So this is the correct statement, and just go and check character table lectures in our courses, and we have the best concepts lectures there. Okay, right. And according to great orthogonal theorem, the first statements, which simply represents the number of irreducible representations, is equal to classes of symmetry operations, and that is the correct statement. Next one, for a diatomic molecule AB, the energy for the rotational transition from J is equal 0 to J is equal 1 state is 3.9. The energy for the rotational transition state from J is equal 3 to J equals to 4 state would be. Now we need to consider from J is equal 0 to J equals to 1, and that should appear at 2B equals to 3.9. So from that B equals to 1.95. Now energy difference between J4 to J3 can be taken as because here B is equal to 1.95, 20B minus 12B result 8B. So 8 into B 1.5. So 8 into B simply 15.6 centimeter inwards. Okay. Next one, for the vibrational Raman spectrum of a homonuclear diatomic molecule, the selection rule under harmonic approximation is, here delta V equals to plus or minus 1 is the correct selection rule. With increase in temperature, the gives free energy for adsorption of a gas onto a solid surface. So here, so whenever we see adsorbate, that is simply absorbing gas onto adsorbent, this is the surface of adsorbent. So adsorbate is normally gas. Okay, so many times it is a gas, right? That's why, which is in random state, so the entropy of adsorbate is high before going to adsorbed on the surface of adsorbent. So whenever the gas is adsorbed on the adsorbent, then it has a systematic adsorption on the surface of that adsorbent. In that case, entropy decreases. Okay, so here delta S is decreasing. Okay, right. And at the same time, the energy, the surface energy of adsorbent also decreases whenever adsorption is taking place. Okay, and that decreasing energy is in the form of heat. Okay, so that's simply related with enthalpy change, that is delta H. Okay, from these two relations we need to find Gibbs free energy, that is delta G is equal to delta H minus T delta S. Okay, so we know that for spontaneous reaction delta G should be negative. Okay, in that case delta H must be high value. Okay, and T delta S must be more negative. Okay, so whenever temperature increases, okay, whenever temperature increases, now delta G becomes more positive from the negative value. That's why here third statement is the correct one for the given problem. Okay, right. Thank you very much.